Hello and welcome to the Engineering Dynamics Course Companion. We're in Class 10, continuing with the kinetics of particles, and today we're going to cover impulse momentum method. With all of these videos, you could always go to the description below, and there's a table of contents, and you can just click on the area there where you can go directly to the example. Okay, so we're started with the bottom line up front, and we're going to use green today. That's a good educational color. We have linear impulse, and we'll define the impulse as force times time. More specifically, it's the integral of the force for increments of time, because the force might not be constant. So if we want to find the total impulse, for instance, if there's a force and time, and it has some type of time of varying nature to it, we would find the impulse was actually going to be the area underneath that curve right there. So that's what linear impulse is. You can also think about it as if someone's pushing something. For the amount of time that they're pushing it, times that force, that's going to be the impulse. And that impulse is going to create momentum. Now, we already kind of know what momentum is, right? It's just by its nature, you get the idea from the word. But as a definition, we give it a letter that's a capital L, and make sure we note that it's a vector, right? And it's going to be mass times velocity, right? So, like something has momentum. If it's a big, large thing that's moving, it's hard to stop it because it's got momentum. It's also hard when it's with a large mass to get it to start moving, right? So we apply a force, F equals ma to accelerate it, but what we're trying to do is give it momentum, right? And so the relationship between impulse and momentum is we have the momentum before plus the impulse is going to be equal to the momentum afterwards. And impulse momentum involves vectors, right? So that's an important difference between that and work energy that we just covered in the previous class, in classes 8 and 9. So, work and energy, they're scalars, whereas impulse and momentum are vectors. Impulse momentum with kinematics can be used instead of Newton's second law or work and energy. Right, so there's some interchangeability in the kinetics problems. All right, so one thing we should review is we had kinetics so far in classes 6 and 7. We covered Newton's second law for kinetics. In classes 8 and 9, we had work and energy for kinetics, and now we have impulse momentum for this is going to be class 10, right? And so 10, 11, and 12 are also kinetics for impulse momentum. So here, that was the bottom line up front. Talked a little bit about it as an introduction. Let's make a connection between Newton's second law and what we were just discussing, right? So Newton's second law can be rewritten, as we mentioned, I think back in class 6, as the time rate change of linear momentum. Like the sum of the forces is equal to the time rate change of linear momentum, right? And we noted that when the mass was constant, right, that was mass times acceleration. But we could rewrite this and rearrange it, and when mass is constant, as the sum of the forces times dt, right? We could take that dt and move it over to the force side of the thing. So that right there is simply enough is our impulse and momentum equation right there, right out of Newton's second law. So you can see the connective tissue right in there. We also saw the connective tissue that was working with work and energy. So go back and take a look at that as well. Another way of writing this, we could just by shorthand saying the impulse is an IMP. And this equation says momentum before plus applied impulse equals momentum after, right? So Newt Dog takes a look at the Wormy with a bunch of his brethren apples. Where's Wormy? Right over here, right? So, oh no, what are you doing? Okay, I didn't give you a voice before, so that's something new. And Newt Dog pushes onto the apple cart right there, and he gives it momentum, right? And you could feel, like, get the idea that that this act right here, right? This guy is going to be this momentum before, which is 0. Here is the act of the applied impulse, and right here is the momentum afterwards. So that's supposed to be the visual mnemonic to try to say, with impulse momentum, think about pushing this very large mass apple cart and to get it started, right? And we make a diagram that's similar to what we've done previously. And these diagrams can really help us to try to organize our thoughts. So we have the initial momentum diagram, we have the impulse diagram, and we have the final diagram. Let me erase these little circles that were getting in the way. And you could see what we're doing here is we're labeling, and once again, we want to make sure we remember that these are vectors, right? There's a vector aspect to these. So we have, we're defining a coordinate system, and we're making a graphical depiction of this equation with our picture here. And we have the impulses that are happening onto the thing, and then we have the final momentum, right? And also note that because they're vectors, we could write out 2 separate equations, right? So for a lot of problems, you could think of like the number of equations and the number of unknowns. We know that that's something that we want to try to look for as a strategy to try to solve some problems. Okay, so here's the example. This is the same example that we covered in class 6 and in class 8. But now we want to show the interchangeability in some situations. Not all of them can you use every method in kinetics, but these are all kinetics, all 3, the Newton's second law, the work energy, and the impulse momentum. So we're using them all in the same problem. So we have this force, this constant force P, that you could barely see because of this thing right here. And I wonder if I draw a mustache on myself, if that'll show up. I don't know. That'll be weird. We can get rid of that. Okay. So we have this constant force P of 50 pounds that's applied to the box that weighs 25 pounds, and that's starting from rest and positioned on this slope where this is 25 degrees right here. And that we have a coefficient of static friction of 0.25, which we're not going to use this time. We used it in example 6 to show that it would move. All right. And then we have a coefficient of kinetic friction of 0.2. And the force that's being applied, it is located with 15 degrees from horizontal. And we want to determine the distance up the slope that it's going to go when it reaches 3 feet per second. Okay, so we want to put together a free body diagram, an inertial response diagram, or usually it should be IBD. Some books call it IRD. I think I accidentally changed it to IRD. I like IBD because it matches FBD. So anyway, we put these together there simply so that we could make sure that we're finding the normal force, right? We want to be systematic here. So we used the FBD portion of it, and really only in the y prime direction, so that we could find what this normal force is. And then we assume it's moving, but we did find that it would be moving in example 6.1 or class 6. So we find the multiplying the normal force by the coefficient of friction, we get the friction force. And now we draw the impulse and momentum diagrams, right? So I start out by just drawing the box and the pluses and the equals, and we get a coordinate axis so that we pick it. Once again, x prime and y prime is a good place to start. We notice that so I guess I accidentally put it there. I put the impulses on here first, right? We put all these forces, and remember now, because all these forces are going to be constant, and therefore, instead of having the integral of the force times dt, we could just write the force times delta t. And how do we know that? Well, for one, there's going to be a constant. This is a constant force. The weight is constant. So the normal force has to be constant, and therefore the friction force has to be constant. But we have to be careful that we don't just jump and assume this, right? We want to take every problem, we want to take it individually and start picking apart and trying to decide, maybe a little argument with ourselves whether it's going to be or not. And so the momentum, when it starts out, right, can only move in the x direction, but it's starting from rest. So the moment here, the momentum is, the momentum is 0 in the beginning. And then so we really want to find the momentum afterwards right here, right? So what we can do is we write out our equation that corresponds with the x direction here for the impulse momentum, and get that out of the way. And we look at this carefully, right? And it's only in the x direction, so we want to make, that's where we have to have the cosine of theta 1 plus theta 2, right? And that's also, we want to make sure that we only have the x direction of the weight, right? The weight's going to be going down a little bit down the slope. And then we have this friction force is also going to be placed right there. And make sure we don't forget to put the delta t's in there, because this is not just force, it's force times time. So we know everything except for that delta t. So now we can find the delta t. So it's very quickly, it's like 0.1388 seconds, all right? So from kinematics now, we can find what that acceleration is, right? We have an initial velocity and a final velocity. The initial velocity is 0 right here. So we can find what the acceleration is going to be, right? And now from that acceleration, we can use the distance from this other kinematics relationship right here, right? I always think of them as the wild cards, the one that we forget about, right? So if we go all the way back to class 1, you'll remember that we had that acceleration relationship where it was the acceleration is equal to v times dv dx, or ds in this case. We're just calling s because it's s. In any case, it's the extra kinematics equation we often will forget about. So we can solve for that distance, and lo and behold, we get 2.5 inches. If you go back to the previous examples, you'll see that we get the same result. So look back through these and make a comparison between these different methods. It's pretty interesting. Don't you think so? Yes, we definitely think. Both of us agree. It is interesting. So here you go. For more examples, check out the Engineering Course Companion right here. Parts 1 and 2 available from Morgan and Claypool Publishers. Take a look down below for links to the books. It's also available on Amazon, by the way. So you could do a search for them on Amazon. And please subscribe to the channel because there will be maybe more videos to come and some updates and that type of thing. And feel free to add comments and suggestions. One thing I had often thought is I like to, these cartoons are meant to be memorable and to add to the experience and to help you retain some understanding. So if you perhaps had some suggestions for a cartoon for the future, I'd love to hear it. And if I happen to use it, I'll make sure that I give credit to where credit's due. So that's it for today, and have a great one.